Hello friends, welcome to a new chapter, chapter 5. I'm going to introduce you to two 17th century mathematicians who made us advance in the knowledge of prime numbers, the Frenchmen Pierre de Fermat and Marin Mersenne, contemporaries and friends. Both mathematicians gave rise to the so-called Fermat and Mersenne numbers, two sets of numbers that promise to have very interesting properties. For its usefulness in the creation of algorithms to find prime numbers, Mersenne numbers became very famous and important and are used a lot today. But this doesn't mean that Fermat's work was inferior. Pierre de Fermat was an excellent mathematician, author of the very famous Fermat's last theorem, which was proved in 1995 by the British mathematician Andrew Wiles. We will meet him again in future chapters. Pierre de Fermat, an excellent mathematician and lawyer, in a wish that was not satisfied in previous centuries about how to generate prime numbers, devised what he believed satisfied this desire, a formula that would give prime numbers. Not all of them, of course, although only primes. These were the so-called Fermat prime numbers. The non-proven conjecture was that the following sequence of numbers 2 raised to 2 raised to n plus 1 only generated prime numbers. That is, making n equal to 1, 2, 3, 4, etc., the result of the operation of raising 2 to the power of the result of 2 raised to n plus 1 would give a prime number. Let us see what happens with a sequence of Fermat numbers. For n equal to 1, the result is 2 raised to 2 raised to 1 plus 1, that is 5, which is a prime. For n equal to 2, the result is 2 raised to 2 raised to 2 plus 1, which it is equivalent to 2 raised to 4 plus 1, that is 17, which is a prime. For n equal to 3, the result is 2 raised to 8 plus 1, that is 257, which is also a prime. This looks promising. Here is where Fermat began to get inspired. For n equal to 4, the result is 2 raised to 16 plus 1, which is equal to 65,537, and it is also a prime. Fermat, filled with joy, went into a tailspin. What if n equal to 5? This is what would happen. 2 raised to 2 raised to 5 plus 1 is equal to 2 raised to 32 plus 1. The fifth Fermat number has 10 digits, and its value is 4,294,967,297. Is this number a prime? Here Fermat has no answer, because the mathematical tools available at the time prevented him from knowing so. But possessed by an astonishing arrogance, and knowing that no one would contradict him, at least before his death, he conjectured that it was also a prime. And not only the fifth number, but, for that matter, all the rest should also be primes. The sixth Fermat number already has 20 digits, and the eighth Fermat number is already greater than the number of atoms in the universe. Fermat numbers grow extremely fast as exponent n grows. Fermat conjectured that all numbers generated by his fantastic formula had to be primes, and so they became known as Fermat prime numbers, and no one would dare question it. But, dear friends, 1 century later came the great Swiss mathematician Leonhard Euler, and nothing escaped him. he realized that the fifth Fermat number was divisible by 641. So the following could be written. So it was not a prime. How did Euler do it? Well, out of curiosity with skill and patience. Thus, he proved with a counterexample that the conjecture was false. But by then, Fermat's prime numbers had already been engraved with golden letters in the history of mathematics. In fact, only the first 4 Fermat prime numbers are known. There may be more, sure there are more, but they are not known. Despite the mathematical talent of Fermat, who went down in history mainly because of the enunciation of his last theorem, here he failed. Moved by the same interest, the French monk and mathematician Marin and Mersenne, contemporary and friend of Fermat, conjectured another idea also based on playing with the powers of 2. He established that the sequence of numbers 2 raised to n minus 1, where n was a prime number, should generate prime numbers. This sequence, for the first value of n primes 2, 3, 5, 7, 11, is as follows. The first 4 are prime numbers, but 2047 is not a prime, as it is a product of 23 and 89, so that not all values of n cause the formula to provide a prime number. This was, of course, annoying to Mersenne, as it broke the beauty of conjecture. Aware of this, Mersenne stubbornly dared to say that his formula would always give a prime number for the following values of n: 2, 3, 5, 7, 13, 17, 19, 31, 67, 127, and 257. And here is the astonishing part, because Mersenne did not prove it. He could not do it. Besides, how could he boldly say that 2 raised to 257 minus 1 was a prime number? This number has 78 digits, and Mersenne did not have a clue if it was a prime or not. Later, already in the 20th century, he could be found that Mersenne was wrong when n was equal to 67 and 257. In addition, he had left alone the path to his formula the primes values 61, 89, and 107, which did give prime numbers as result, and that he did not consider. That is, Mersenne was another daring person when it came to making conjectures. What happens is that, unlike with Fermat primes, those of Mersenne have been very useful. We do not know how many Mersenne primes numbers exist, but they are abundant, and it turns out, and I will not go into detail, that there is a relatively fast method to know whether a Mersenne number is prime or not. Relatively fast means working with computers today, but still fast compared to other potential prime numbers. Thus, it is not surprising for prime number hunters who want to undertake a new challenge to work with potential Mersenne prime numbers. We saw in last chapter that number is a prime number, the largest known prime number at the time I make this video. This is a Mersenne prime number, where n is equal to... Dear viewer, the last chapters have been a presentation of the prime numbers. We have started by knowing their features and their seemingly chaotic behavior. We have seen why, from the beginning of mathematics, they have aroused so much curiosity. A race of research began centuries ago, reaching our times, and for now there are no signs of it coming to an end. There are many unanswered questions. Many paths to knowledge have been opened during hundreds of years. We will follow several of them throughout the chapters, and they will lead us to the most beautiful landscapes. The best way to start with the walk is to learn about the life and work of one of the best mathematicians of all times, who made significant progress in the understanding of prime numbers, the great Leonhard Euler. But this will leave for the next chapter. Thank you for watching.